Okay. First of all, let me thank the organizers for giving me this opportunity. And I'm going to go back to basics. We've been talking about failure, plasticity, fluidization. I'm going to take you back to actually trying to understand elasticity. And the title that I gave is Emergent Elasticity in Non-Thermal Solids. Think of this as an alternative paradigm to the classical theory of elasticity. And I would argue that in the kinds of systems that I'll actually talk about today, this is the only rigorous paradigm. The classic paradigm of elasticity is not applicable. And then to this audience, listening to all of the talks over the last 3 days, I've been thinking a lot, and I think there are some systems for which maybe this alternative paradigm is better adaptable than the classical elasticity paradigm. So it's worth thinking about. So as I go along, I'm going to try and point out where I think there might be connections to things that I have heard about. So first of all, the people that have done the work, Jishnu and Mike Dion, were my graduate students at Brandeis. Kabir was a former postdoc who's back in India. And really, this thing was driven by my discussions with Shubhra Bhattacharya at ICTS in Bangalore, who's a hard condensed matter physicist. And he knew me from my days of hard condensed matter. So I was giving a talk, and some of the people here know that I've been sort of trying to come up with alternate theories for many years now. So he knew about that, and I was giving a talk, and he said, oh, but do you know about these new theories of the kind that you worked on many years ago? I said, no, what new theories? And that basically drove this whole development over the last 4 years now. So what am I talking about? So this electron micrograph here is cornstarch. So this is the kind of thing that we're going to talk about. So the question is, if I'm trying to think about particles like this, which form solids, how do I think about this, right? So how do I think about this? So, okay, it just takes a while. Okay, so the kinds of systems that I will talk about specifically today are particles like this, or entities. They don't have to be particles, they can be cells, which interact via all kinds of, their interactions are not well defined. So in this system, for example, right, if I have two particles, I don't know what their interactions are. Because if I rotate a particle, the surfaces that touch each other change. So the interactions are indeterminate. So thinking about potentials and interaction potentials seems like it might be worth doing. People do tribology, but maybe there is a better way to think about it. And what makes this particularly troublesome is there's no non-Brownian, there's no Brownian motion in these, so nothing gets smoothed out through thermal fluctuations. So basically what you have here is what you get. So what do we do with things like that, right? But I'm going to focus on systems. So I'm going to think about solids. So for this to be a solid, at least what I know is each of these entities are under force and torque balance, because otherwise they would have moved. So they're static. So there's a mechanical equilibrium underlying this. So what do we try? What can we do? How do we construct field theories? So I'm actually going to attempt to construct a continuum theory that can describe the mechanical properties of such systems. And because I'm saying this is an alternative paradigm, I need to tell you what the usual paradigm, remind you of what the usual paradigm is. And sometimes we forget, very well-established theories, we forget what the foundations are and what are the approximations we make to get to there, because we apply them. So we just apply them. We think they work all the time. So classical elasticity is one of the oldest known field theories. it predates us knowing about crystals and atoms, but from the modern perspective, we know that emerges from broken symmetry. Generalized elasticity, any kind of rigidity that's described by classical elasticity paradigm, strain and stress and displacements, come from the fact that I have broken a continuous symmetry. So crystals have broken translational symmetry. That's why you have phonons, you have what are called Goldstone modes, and from that, you can coarse grain up to classical elasticity theory. It might not be essential to justify the continuum theory, but I want you to remember that that's where it comes from. So, but in a continuum sense, this is what I have, right? I think about a reference state, which is stress-free and strain-free. And I want you to remember that. So elasticity, continuum elasticity says this square has no stress and no strain. And then I strain it, and then there's a stress. And then if I take the stress out or the strain out, it goes back to this identical reference structure. So there is a unique reference structure. So the equations then of classical elasticity theory that tell me how to figure out how stresses get transmitted in a system like this start basically from momentum conservation or force balance. So the sigma here is my stress tensor. So the divergence of the stress tensor has to be equal to whatever the external forces are. The stress tensor is symmetric. You can think that comes from the torque balance. So if I just had these two equations, I don't have enough equations to solve for the stress transmission. So think in 2D. In 2D, sigma has 4 elements. That tensor, it's a 2 by 2 tensor. It has 4 elements. There are 2 equations embedded in this, and 1 equation for the symmetry. So I don't have enough equations. So where does classical elasticity theory get its other equation from? And that relies on the fact that I actually have a strain. And the strain is defined from this reference structure. The strain gamma ij, and I know I'm saying things that are very obvious to people and people know it, but I need to tell you why that this is the foundation. So the strain is defined as derivatives of displacement from this reference structure. And the displacements are vectors. If I define a tensor this way, you can show mathematically that the strain tensor satisfies this equation. It's a weird way of writing. It's a double curl. Okay, so this is known as the compatibility equation in elasticity theory. Okay, so that closes the loop. So what I need is this equation, that's about stresses, this equation. So strain in some way provides me with this equation. And then in normal thermal solids, I would say the stress is a derivative of the free energy with respect to the strain. And then I get linear response. It could be also nonlinear response. This thing could depend on gamma, but I still have a relationship between stress and strain. And once I have that, then I have enough equations to solve for stress transmission. Okay? So I need this compatibility equation. It's absolutely essential for me to have that compatibility equation for me to have the full framework of elasticity theory. Plasticity then comes from violating these equations, the compatibility equations. So in normal crystalline solids, these define defects. So Max was talking about 5-fold, 7-fold. These are disclinations. Disclinations are defined by the violation of the strain field around them. I go around a disclination, I do a loop integral, I get a non-zero value. So the double curl is non-zero. This particular incompatibility, which I would call the geometric incompatibility, has also been used to try and come up with definitions of defects in amorphous solids. That this kind of geometric incompatibility should be used to understand what are defects, what can drive plastic flow in amorphous solids, right? Because in crystals, it's these defects, disclinations and dislocations that drive plastic flow. Okay, so this is all good. Now, the kind of system that I am interested in understanding are what I call jammed solids. And again, here I'm going to be very careful. I think Max mentioned this, that jamming is used in, it's become part of our language, and it means all kinds of things. I'm going to use it in a very precise way. And the precise definition I'm going to use is the one that was used in this PRL in 1998 by Mike Cates, Joachim Wittmar, Jean-Philippe Bouchot, and Pierre Clonon? Philippe Clonon, yes. The jammed solids are ones whose solidity stems directly from the applied stress itself. So think about that. It's basically saying, and I think Sri talked about pre-stress, there is no solid without pre-stress. These solids don't exist unless you put some stress on them. So these are photoelastic images from Bob Berenger. So if you think about sand, in some ways it's easy to understand. The sand has no cohesion between it. They just resist compression. So unless I push them together, why would they want to stay together, right? So here, gravity is creating the solid. This is what you see in these photoelastic beads. And then this was Bob's way of probing the response of these systems by putting in a force. And what he showed is that if you measure this response, so if I subtract this from that, this response is reproducible in the sense that I can do a disorder average. I can take many configurations with this identical setup, and the distributions are reproducible, and I can actually define an average response. But if I change the setup, that average response might change, right? But this is happening in a system where strain doesn't mean anything, because I have no stress-free state, no unique stress-free state. Every stress-free state that I have is its own some random state. Similarly, here you have heard about DST and shear thickening, and this is another clear system. So this is stress, this is packing fraction, and this is shear-jammed. So if I put a suspension like cornstarch up here and I reduce the stress, it will flow, right? This is not something that we expect from classical elasticity theory. Things flow under a stress. Here I need the stress to create the solid, and then I have to take the stress away to make it flow. Right, so what do we do with systems like this? Okay, so the central sort of problem was articulated again by Cates and Bouchot in the early 2000s, saying that we don't have this compatibility equation. I've written it down here, but that's basically the problem. If I cannot define a stress-free state and I cannot define a strain, I don't have the compatibility equation. So can one come up with a stress-only formulation of elasticity theory? That was the question they posed. And I have been struggling with that since 2010, since my former student Silke Henkes, who is now very much part of this community, it was Silke's thesis where we first tried to figure out what that could be. And we were not the first. This problem of the missing equation have plagued people since the 2000s. And people came up with all kinds of ad hoc solutions, including us. What I want to convince you today is there is a rigorous way of getting to this equation and to a stress-only formulation of elasticity theory with no mention of strain. Okay. So this is just, I'm only going to look at networks which are in mechanical equilibrium. So force and torque balance are certainly satisfied. So what I have here is a system which is highly constrained, right? These constraints have to be satisfied at every contact, right? So these are local constraints. It's highly constrained, but it's highly degenerate. What do I mean by that? I can come up with lots of configurations. If you give me, billions of particles, there are lots of configurations that satisfy these constraints. So I have high degeneracy, but each configuration in this highly degenerate ensemble, exponentially large number of states, let's say finite entropy, has to satisfy these constraints. So how do we think about these systems? This is not something we have done very well within the soft matter community, but the community that I came from, this is a challenge which has been addressed repeatedly, and there are well-defined ways of thinking about it. So I'm going to take you there for a minute, but at every point, I'm going to try and map it onto things that I think are understandable to this community or you'll connect to. So what this task that we set ourselves, Shubro, Kabir, and me, is can we construct a field theory that imposes these kinetic constraints rigorously, exactly, to construct equations that will predict the stress state of the system.
FT.
Sorry. Yeah, so if I have friction, this is just the static friction.
So, but you're assuming that this phenomenological law, which is valid macroscopically.
I don't know, I'm just saying it. No, it's not macroscopically. It's at every contact.
Yeah, but I mean, that's what I'm saying. So normally we study this thing for macroscopic surfaces.
So this mu might be varying at every contact, etc., right? Whatever. But there is a constraint. Think of it that way, right? There is a constraint.
Okay.
And it's an inequality constraint.
And the second question, it doesn't need to be a dry contact. Because normally, again...
No, you can make, the constraint. So I think the main point, you can even ignore what precisely these constraints are. I think the point I'm trying to make is constraints are the god here, all right? So constraints determine everything. Whatever constraints you put in, it could be that there are liquid bridges that break, so then you have to put in. Now, thinking about hearing all of these talks, there are cellular junctions where things might, they might detach. So there are some constraints that change as a function of time. All of that can happen. But let's think about the simplest situations of where, and I'm not going to actually specifically use these contacts. The main point is that there are constraints, sorry. This one actually causes lots of problems. This one also does, but doesn't show up qualitatively. Okay. So now I'm going to take you to a toy model, which comes from, doesn't matter where it comes from. Think about these honeycombs and some arrows on them. And I have a constraint, and I'm going to put this in right here. And you can think of the double arrows as pre-stress. Think of a system where because of frustration, you cannot get a solid where there's no pre-stress. Or in this system, because of frustration, I cannot get a configuration where there are no double arrows. But I know that there is sort of a minimal way of meeting the frustration, which is that at every vertex, I can have only one double arrow. If I have more than one double arrow, I haven't done my best constraint satisfaction problem. So I'm looking at configurations where there's only one double arrow at every vertex. Now, I can have many, many types of configurations like this. This is particularly one where the double arrows are sort of random, but as you can see, there's only one per vertex. This is one where the double arrows are ordered. So I can have anything. I can have ordered arrangements, disordered arrangements, but I cannot violate this constraint. So think of this as a simple example of constraint satisfaction. So how do people know how to construct field theories that describe the rigidity of these systems? So how do people go about that? And again, I'm going to do this in one slide. So what you do is associate a variable with these double arrows, which you can think of like a discrete magnetic field or an electric field, which is saying if I have two double arrows going up, then this is an E field of magnitude 2 pointing upwards, and these arrows are E fields of magnitude 1 that are going outwards. So what I have done is I have mapped this constraint, which was a very geometric constraint, into an algebraic constraint saying the fluxes have to add up to 0 at every vertex. Right? This is something that I can write down in an equation instead of drawing these geometric pictures. So the total, and if it's not obvious, I can explain later, but it's probably obvious that, so at every vertex, the flux has to add up to 0. And if I look at the total flux along any row, so let's look at this row. There are 2 going up, 2 going up, 4 going up, 2 going down. So there's a total flux of 2 going in the vertical direction. That has to be exactly the same in every row. So there's sort of a global consequence of this local constraint. That this, if I measure the flux at the boundary, I'll find that the vertical flux is 2, and it's that true at every vertical layer, at horizontal layer of my system. I cannot change it. So this is a kind of conservation law that emerges from the constraints. So this is something that people worked out. What you can show then is that you can coarse grain these systems. The flux adding up to 0 at every vertex, and if I call this an E field, I could have called it a B field, doesn't really matter, it's some vector field, its divergence is 0. That's the coarse-grained representation of this constraint equation. And then this gives me an emergent electromagnetism. This is the Gauss's law for some kind of ENM, and this is how these kinds of systems are dealt with in a field theory. So I write down a Lagrangian, which is like if there was dynamics, I would add a B square here. This is the usual electromagnetic Lagrangian, but it's not an electric or magnetic field. It's taking the constraints and creating an effective representation, which it will not be so hard for our system. But and this stiffness constant, this tells me how hard it is to change the electric field, depends on what is this total vertical flux. So here, this total vertical flux is 4 minus 2. Here, it's maximal. It's the maximal that I can get. So the stiffness depends on whether I'm in this sector or that sector. It sort of depends on the entropy, how many states I can put in each of these. Okay, so this is story. This is this story. Can we construct a similar framework based on our force and torque balance arguments for solids? And very important, when I say that this is true, it's only when I average all of my allowed configurations. It's a kind of disordered average theory, and that's very, very important to remember. And how do I average? The assumption here is that every configuration that is allowed by the constraints is equally likely. So it's like a kind of a microcanonical ensemble or an Edwards ensemble for the granular people. Okay, so I'm going to go through this quickly, but this is the picture that I want you to keep in mind. So I'm going to represent the kinds of solids that we have. Because they don't exist without external forces, my black arrows tell me there are some forces. These forces actually create the network that exists inside, the contact network. If I didn't have these forces, if I put a bunch of sand on this floor and I didn't put forces on the boundary, they will not make contact. So the contact network is created by these forces. Once they're created, then I have forces on every contact. I can define a contact level force, then contact level torque. I can define a force moment tensor, which upon coarse graining gives me the stress tensor. So that's all part of what we need to do. So, but I can define a coarse grained stress tensor, which is computed out of this. So within this red box, let's say, I can tell you what the stress tensor is if you tell me what the forces are and where these contacts are. One thing that I'm not going to talk about at all is torques can actually live on the boundaries, but that's not important for what we're going to talk about today. So what can we do with this? the question is there an existing field theory that actually lets me impose these constraints, the force and torque balance constraints? And it turned out that in 2018, a graduate student at MIT constructed an analog of E&M where the E field and the B field are tensors and the charges are vectors. And then again, because I want to get to the crux of the problem, there is a full set of Maxwell's equations, just like in E&M. So there's an E field, there's a B field, there's an electric charge, there's a magnetic charge. Remember, these are not actual E and B fields, right? These are some emergent things. So there's nothing saying I cannot have magnetic monopoles. And then there are these curl conditions, and this should remind you in some way of the incompatibility condition that we are struggling with. Okay. One thing that we had to think about, because as I said, in the kinds of solids that we are thinking about, the contact networks are created by the force itself. So this is all theory in vacuum. I actually have a polarizable material from this perspective, in the sense that if I put an electric field or charges at the boundary, I can actually create charges inside through so think of this as a dielectric. So I'm going to rush. So you have to trust me that using all of this, we can map our solid problem into this with the following mapping. So in a dielectric version of the E&M, I would have the divergence of the electric field has a free charge and a bound charge, so the bound charges are inside. In our mapping then, what happens is these bound charges are the contact forces that develop in response to these charges. These are the free charges. So if I put all of this together, I know I'm rushing, this is what I get. So I've basically used the Maxwell's equations, the static version of the Maxwell's equation in a dielectric. So I don't need a B field. I set this to 0. I'm missing one slide. So what I want you to do is forget about this equation, set the right-hand side of this to 0, ignore that equation. This is the static limit of this theory. And the static limit of that theory then gives me, once I do this mapping, the equations that I need for my elastic solid stress-only formulation, because this is the equation, this equation is the static version of that third Maxwell's equation. And this is the missing incompatibility equation, but this is not strain, it's still stress. There is a stress which is coming from screening of the external stresses due to internal contacts developing. So there are sort of two kinds of stresses, just like I can have a E field and a D field in an E&M, a polarizable medium. So these are both stresses, but this one I can't really measure. I can only measure this because this is what I control. And then if we just assume that there is a kind of linear relationship which is coming through the polarizability, then these are emergent elastic moduli. So let me just summarize where this theory is, and then I want to end with just one more slide. So it looks exactly like classical elasticity theory, but there's no strain here. And so in classical elasticity theory, this would be the strain, these would be the displacement fields. Here, these are not physical variables. Only this is. This is just like, if I told you at E&M, the electric field is a gradient of a potential, this is that, right? So it's like the analog of an electric potential. It's measurable differences. The differences of it are measurable, but it itself is not. So it's not a physical field. What is absolutely measurable are E and sigma, right? So there is no measurable displacement field here. The elastic moduli are not material properties. They're determined by how polarizable my system is. And I was listening to talks throughout about the biology. And if there are things happening at the cell junctions that make it more or less susceptible to external stressors, from my perspective, I'm making the system more or less polarizable and could be very heterogeneously polarizable. They don't have to be the same. You know, this thing can be depend on position, etc. It can be, right? So here I've written it simply as saying there is no local variation, but there's no problem. I can write down a Lagrangian where this depends on position. Okay, so what I want you to leave you with is after much, much work, we've been able to show that in jammed systems, jammed frictionless soft spheres, things that Sri has done many, the strain incompatibility and the stress incompatibility are completely different. And this has come from work by Xiaoming Ma, student Jose Tavares. And what we were struggling to do is in a discrete network, figure out how to show this double curl condition. So he came up with two ways of doing discrete loops. One, to measure the strain incompatibility. And the strain here, and this is important, in a jammed system, the only reference state you have is the particles are just touching. There is no other reference state. So you start from there and you define a strain. And then what he's showing here in a particular representation is the strain incompatibility. And what you see is that if you're very close to the system being unjammed, so not too many soft spheres are overlapping, the incompatibility is very small. As you go to more and more jammed states, this geometric incompatibility, the strain incompatibility is very large because basically I've taken a hard sphere system and overlapped it. If I now want to go back to the hard sphere system, this thing doesn't fit in my box. I have to buckle out. So that's basically what this geometric incompatibility tells me. Now, in a more complicated way, he has figured out the same thing for the stress. But now, a crucial difference is that these discrete loops now don't live in this network. It lives in a kind of dual network that I don't have time to go into. I have said it here. But here, this is a state here. So it's this configuration or a set of configurations here. And what he is measuring is this average double curl of the stress. And if you average over configurations, and if you look at larger and larger loops, for very small loops, you see huge fluctuations, the stress is completely compatible. So where the strain is most incompatible, the stress is most compatible. So this is telling me in a very direct way that strain and stress are not related in these systems. And you really need to think about stress because the hard sphere is not a good reference structure for these systems, basically, in some way. So with that, I'm going to just end. I forget. Okay, so there. So I just wanted to end with this quote from an article by Kadyrov from 1999, where he said, one might even say that the study of granular materials gives one a chance to reinvent statistical mechanics. And I'm going to say here it gave us, I think, a chance to reinvent elasticity theory. Okay, I am done. Thank you.